Hello and welcome back. Of course, one of the most famous non-smooth settings for analysis and metric spaces is that of self-similar sets and Cantor sets. Some people also call them fractals, but technically there isn't a universal definition of what exactly a fractal is. So to keep things simple, I will do a case only in dimension 1 in this video, and in future video I will also do some Cantor sets in higher dimensions. But the general idea, of course, will be similar. And the good thing about this video will be that we will see, for some of you, maybe this will be the first time that you see sets with Hausdorff dimension are not an integer. So of course we are familiar to collection of points, zero-dimensional, line segment, or just any connected subset of R1 has Hausdorff dimension 1. There's then the plane, and the manifolds have also integer dimensions, but maybe this will be the first time you ever see a set whose Hausdorff dimension is not a natural number. Okay, let's start simple. We begin by the unit interval in R1, and then we fix some real number in 0 and 1/2. So by the way, I'm following the book by Mattila. The title is Geometry of Sets and Measures in Euclidean Spaces. The subheading is Fractals and Rectifiability. So the edition of the book I have, this is in chapter 4, and I will follow his notation, and for further details about what we will talk, you can refer to that book. Okay, so we will construct a Cantor set corresponding to this lambda. And how we do it is quite easy to explain. So you have 0 and 1. You will remove from your Cantors, from your interval, a central subinterval, so that the remaining two intervals from here to here each will have length lambda. So hopefully these look as if they have the same size. That is what I intended to do. So this will be not in the Cantor set that we will build, and so these two on the sides will be in the Cantor set. So far we have only, so say I1 union I2, but you can also say this is the two subintervals at level 1 of the construction. But this is not, of course, our Cantor set, because this is just union of two intervals. What will happen is we will continue analogously. So from each of these green intervals, we will remove a middle interval with the same ratio of lambda. So we will be left with 4 intervals, and there will be this and this. So we removed the middle from here, so we cut this out. So that will be outside the middle, and Only the green part will be here. So this will be level 2 intervals, and there will be 4 of them. So you have I2, 2, you have I2, 3. So I'm using superscript to say what level I am, and then the subscript is just counting or indexing, say from left to right, all the subintervals. So my counter set that I will build, and it will depend on lambda, will be ultimately a subset of all these levels. So then you continue forever. Therefore, precisely this C lambda will be, okay, it will be inside all levels. So you can say K is the level, so K1 to infinity. And what is the subset at level K? It's union of some intervals of this type. So I going from 1, and it's easy to see that there will be 2 to power K many subintervals at level K. So at level 1 we have 2, at level 2 we have 4, so on. So you first take this union, and then you take intersection. A question that one should actually ask first is, why is C lambda not empty, right? How do you know you will be left with anything? A cheap answer to that is that, well, you have this 0 which remains in every level, and you have this 1 that remains all the time, so at least those 2 points will be in there. But actually counter sets are always uncountable. The answer to this question has 2 parts. Number 1, if K1, K2, and so on is decreasing sequence of compact and non-empty sets in any, actually, Hausdorff, in any Euclidean space, then their intersection is not empty. And the proof of this by contradiction is one of the most elegant proofs I've ever seen. It's such a beauty, the proof of that. And if you try out, just use definition of compactness and it pops out. Then any sequence left, right, any binary sequence, we can say binary sequence of this type corresponds to a sequence of decreasing intervals. I should say, well, compact intervals too. And we have seen this through other stuff we have done in this channel. So initially you had the full interval 0, 1, and then a left would be, okay, the first subdivision puts you in one of these 2 intervals, so you can go to the left, for example, and then in the next level this gets divided into 2 parts, so you can choose, for example, right. So once you are here, you have a choice between left and right, and then you keep going. So and every time you do, it's just that you're selecting a subinterval of the previous one, and all of these are compact and obviously decreasing. So for every binary sequence. So the conclusion from these two is that, so for every binary sequence, there exists a unique point in the Cantor set. And the uniqueness is obvious because once you change any element in this left-right sequence, you end up in a totally different subinterval. In finite time, you already go far away from that point, and you totally change your interval, not like at infinity in finite time, and then there's no way you can end up in the same point as the previous one. So this shows uncountability, but we will discuss the fact that the Hausdorff dimension of C lambda is log 2 divided by log of 1 over lambda. So log of lambda would be a negative number, but this is now the right one, so let's call this just S. And from this also it follows that this has to be an uncountable set, because countable sets have Hausdorff dimension 0, and this is not 0, so therefore the set could not have been countable. But I gave that more elementary proof of uncountability in case you don't want to go through this argument with the Hausdorff dimension. Of course, we have done a whole playlist on Hausdorff measure and Hausdorff dimension, and it's actually one of the most favorite playlists out there, so please do check that if you have not yet. So I'm not intending to prove this lemma. Its proof is included in the book I mentioned, but rather a few interesting points from that. So as lambda goes to 1 from below, remember lambda is between 0 and 1/2, so I meant 1/2. This S converges to 1, which is the dimension of the full interval 0, 1. And that is very plausible because lambda being close to 1/2 means you're removing only very tiny amounts. So this remains, and maybe this remains. So each of them is close to, remember that each of these are lambda, and if lambda is about 1/2, that means nothing, almost nothing is left here, and then that keeps happening for the future iterations also. So you're removing less from 0, 1, and therefore the set is expected to be a larger set, and that is captured by the fact that its Hausdorff dimension gets closer to 1. And of course the opposite direction is also correct. If lambda decreases to 0, then the denominator blows up, so S also converges to 0. And this function of lambda is of course a continuous function, and it has intermediate value. So for every S in 0, 1, there exists a Cantor set with Hausdorff dimension equal to this S. So just by this simple example, you can, for every real number, you can find a set whose Hausdorff dimension is precisely that number. Another issue when dealing with Hausdorff measures and dimension is whether the Hausdorff measure. Now the amount of the measure in that correct dimension of your set whether that measure is finite and positive. If you're confused about this, maybe you should look at this example. So R1 has Hausdorff dimension 1, but the Hausdorff measure of R1 is infinity. So this is a set, so if you try some other value, so if you H alpha of R1 will be 0 if alpha is strictly bigger than 1, because it's alpha is the wrong dimension. It will be plus infinity if alpha is strictly less than 1. And we see that the only hope, of course, well, by definition, Hausdorff dimension is the only number that could produce potentially a number between 0 and infinity, but it doesn't have to. So in this case, we see that even for the right dimension, you get infinity. So there is no measure, no dimension with which we get a positive and finite number. On the other hand, there are sets where this goes with the other direction. So you get 0 at the right dimension. But the answer to this question for our set is that actually, if you compute the Hausdorff measure of these Cantor sets, so this S is of course also S of lambda, if you compute the right dimensional Hausdorff measure, it's actually equal to 1. And interestingly, it's independent of lambda. Of course, this is no contradiction or anything because, well, your set changes. It becomes smaller or larger depending on lambda. But also you compute the measure in a totally different way. So you have different powers. So this can indeed happen. This is a bit more technical, and Mattila's book does not prove this completely. All it proves is that with that S, this C lambda is less than 1, which shows that the Hausdorff dimension is at most S, but then it also proves this side, which means the Hausdorff dimension has to be S, because the only value of S that could produce a finite and positive value is the Hausdorff dimension. Actually, once you prove this, you have captured two things. Number one, that the Hausdorff dimension is actually this S. Number two, that Hausdorff measure is finite and positive. This side is an easy one because of the very construction itself. So you want to cover your set and just count, or you want to bound. Well, you cover by the same line segments that you construct the Hausdorff measure. And then, so you will have length of these to power S, and this count here is exactly the right amount so that this goes less than 1. So you get an upper bound. And usually getting upper bounds is easier for these scenarios because you already know a covering of your set, because your set, in fact, you have the coverings and then you take intersection to get the set. But the lower bound is way more difficult because you have to prove that for any covering you have some you have this lower bound. So proving these are usually very difficult. You have to show that for every covering this happens, but to show this you need to show that there exists some covering. So this is easy. This is often very hard. Okay, and I think this is a good point actually to stop here. There is a twist a beautiful twist to the construction of Cantor set that can make it even more interesting. And I want to save that beauty for a follow-up video. So until then, have a great one, and thanks for watching.